Okay, 5.6 is about differential equations and growth and decay. So just a different method of solving differential equations is going to be called separation of variables. All right, we're going to get the x's on one side and the y's on the other. All right, and I'm going to show you the easier way that I was shown how to solve this problem. Is remember how we wrote a bunch of different ways to write the derivative. All right, so when we took a derivative function, we said y prime equal to, or we said dy over dx, the change in y over the change of x, right? That was a different way. And when you use separation of variables, it's much easier to see it like this. So 2x over divided by y. Let's get all the y's to one side. And well, what I can do is I can multiply each side by y here. We'll multiply by y, and I can multiply by dx on this side, so it cancels out over here. So I have y times dy equals 2x times dx. And then in order to solve this differential equation, we can just go ahead and take the integral of both sides. And this is saying, now remember this, we're taking the integral of y with respect to y. That's what the dy means. And we're taking the integral of x with respect to x. So we got to take the integral of y with respect to y. So we're going to have, increase the power by 1 divided by the new power. All right, equals increase the power by 1 divided by the new power. So I'm going to have x squared. And then actually we're going to have our plus c. And if we wanted to move it all over the same side, we'd have y squared divided by 2 minus x squared, and then either a plus c, doesn't really matter. We don't know what c is, but any constant could be plus or minus. All right, so there's our differential equation there. For example 1, exponential growth and decay. If y is differentiable on a function of t such that y is bigger than 0 and y prime equals ky for some constant k, then y equals c times e to the kt. If you notice, that looks exactly like the PERT formula, which it is. All right, where c is the initial value of y and k is the proportional constant. Okay, now keep in mind this word proportional here. Keep that in mind there. Exponential growth is when k is bigger than 0, and exponential decay is when k is less than 0. All right, so here we go. I have the rate of change, in this example number 2, the rate of change of y is proportional to y. So since the rate of change is proportional, that means it's exponential, all right, to y. When t equals 0, y equals 2. When t equals 2, y equals 4. What is the value when t equals 3? In order to solve this, since it's proportional, the change of y is proportional, all right, that means we're using this up here, all right. They gave us some conditions. They say when t equals 0, y equals 2. So y equals 2 when t equals 0. So we have c times e, t equals 0. We don't know what our k is, our constant is yet, but we're going to end up solving for it. Actually, you know what? 0 times k is going to be 0 no matter what, right? So we have actually e to the 0 power. Well, anything to the 0 power is just 1. So I have 2 equals c. So in fact, c equals 2. And we should have known that already from the definition up here. It says c is the initial value of y. Well, initial value is always when t equals 0. When we're starting out, that's our initial value. All right. Well, I didn't have to show you this part here, but I'm just illustrating a little bit here why that's the case. So far we have y equals 2 times e to the kt. And so we're left to solve for k, and we're left to solve for t. All right. Well, they gave us another set of conditions here. They say when t equals 2, y equals 4. So let's plug in. 4 equals 2 times e. We don't know what k is, but we know what t is. We know that is 2. All right, so let's go ahead and solve. All right, let's solve for k. Let's divide by 2. We get 2 equals e to the k times 2. We know that the natural log function and the exponential function are inverse of each other, so we can take the natural log of both sides and get rid of that e. So I have the natural log of 2 equals 2 times k. And to solve for k, we're just going to divide by 2. All right, so we're going to go ahead and divide by 2 here. Okay, we're going to go ahead and divide by 2. So we're going to take the natural log of, I believe it's 2, right? Divided by 2. Whoops. Divided by 2. And we get 0.346 something, right? So we just solve for our k is what we solve for, all right? And then we're still not done with our problem yet, because the only thing I guess we have left to do is to answer the question. It says, well, what does y equal when t equals 3? All right, so we're going to solve for y. So y equals 2 times E, we solve for K is like 0.345, whatever, all right? We have it in our calculator, so I don't need to write it out. And then times T equal to be 3. So we can just straight up plug this into our calculator and figure that out. All right, so we're going to have 2 times E to the 3 times this number right here. All right there. So when T equals 3, Y is going to equal 5.5 or 6568 in that big, huge number there, and you can see that. Okay, so that's how we solve example 2 there. All right. A little more real life problem here is the half-life of plutonium is 24,360 years. Suppose that 10 grams of plutonium was released in a nuclear accident, kind of like the one that's going over in Japan right now. How long would it take for those 10 grams to decay to 1 gram? Okay, well, we're using that. This is going to be exponential growth and decay here. All right, they give us a couple initial conditions. They give us suppose that 10 grams is released in a nuclear accident. So at time 0, we have 10 grams. So 10 grams is released when T equals 0. All right, so 0 times our K. We don't know our K yet. All right. So again, we just have our initial condition of Y is going to be our C. So far we have Y equal to be 10 E to the KT. All right, well, they give us another condition. They actually tell us what the half-life of plutonium is. They tell us that it's 24,360 years. So in 24,360 years, we're going to have half of the 10 grams. We're going to have 5 grams. So we're saying that 5 equals 10 times E to the K times 5. Or, sorry, not 5. To the, how many years at T equals 24,360. Sorry about that. Okay, so when time is 24,360 years, we have 5 grams left. We can go ahead and we can solve for our constant, then our K. Our constant of decay in this case. All right, so we're going to divide by 10. So I'm going to have 1/2 equals E to the K times 24,360. We're going to get rid of this E, so we're going to take the natural log of both sides. So the natural log of 1/2 equals K times 24,360. And then to solve for K, we're going to go ahead and divide the natural log of 1/2 by 24,360. And we can do that in our calculator right here. So we're going to say natural log of 1/2 divided by 24,360, and we get some ridiculously small number. Okay, and I'm going to move my calculator over to this side over here because we're going to work it on that side here in a little bit. Okay, so we still haven't solved for how long it's going to take us to decay to 1 gram. Well, to answer the question, we want to know when does Y equal 1. So when Y equals 1, all right, we got to solve for T, our time. So we're going to have 10 E to the K, which we figured out was some ridiculous number. All right, I'm just going to write K. We know what it is. It'd be a mess for me to write it. So we're solving for T, okay? Just keep in mind that we know K. All right, so then I would divide by 10. All right, so we want to get T by itself. So I have 1/10 equals E to the KT. And remember, we know K. Take the natural log of both sides. So the natural log of 1/10 equals K times T. And then we know K, remember, so we're going to divide by the K. So we're going to have the natural log of 1/10 divided by our K, and that's going to be T. So let's go ahead and let's work that out on our calculator. Well, looks like I didn't move it far enough. See our equation here. That's right. All right, here we go. So the natural log of 1/10 divided by our K here. All right, notice I had to put that extra parentheses in here to keep that 10 to the -5th down in the denominator. Otherwise, it would have divided by -2 point something and then taken everything times 10 to the -5th. We would have got the wrong answer. Anyway, so when I type that in, it's actually, in order for us to get down to 1, go from 10 grams to 1 gram, it's going to take us 80,922 years, which is quite a long time. All right, so there's one problem there. So here we go. 4 months after it stops advertising, a manufacturing company notices its sales have dropped from 100,000 units per month to 80,000 units per month. If the sales follow an exponential pattern of decline, what will their sales be after another 2 months? Okay. So, it says after 4 months, it stops advertising. So after 4 months, so at time 0, so it gives us, okay, so after 4 months, it drops down to 80,000 units per month, okay? So after 4 months, it stops. 4 months after it stops advertising, manufacturing company noticed that its sales have dropped from 100,000 units per month to 80,000 units per month. Okay, so we're on the right track here. So after 4 months, it drops. All right, so at time 0, before it stopped advertising, it was selling 100,000 units per month. So at time 0, it was selling 100,000 units per month. Time was 0. All right, so again, that gives us our initial condition. We can go through and solve all that, but you guys know how that works. This is our initial condition. So before we stopped advertising, so at time 0, we're selling 100,000 units per month. Okay, so far I have y equal to 100,000 because that's our initial condition, and equals c equals k times t. Okay, well, they give us another condition. It says after 4 months. So when t equals 4 months, all right, our sales drop to 80,000 units per month after 4 months. So e to the k times 4. Well, let's solve for k then. Again, we divide by 10,000, so I think we have 0.8 equals e to the kt, or e to the k times 4. Natural log of 0.8 equals 4 times k. So the natural log of 0.8 divided by 4. So let's do that real quick here. So the natural log of 0.8 divided by 4. And we get negative 0.5. Okay, so we know what k, we just solved for k. All right, so we know what k is. So far now we just solved for that's like a negative 0.4 or whatever. So this is negative 0.4. They want to know now is what it's going to be. All right, what are the sales going to be after another 2 months of not advertising? Well, we're at 4 months here, so another 2 months after that's going to be t equal to 6. Okay, so sorry, we were at 4 months here. Another 2 more months is going to be at time 6. So 6 months after we stopped advertising, we want to know what we're going to be selling per month. So we're going to solve for y. So we have 100,000. All right, e to the k, which we have, which is like negative 0.4. I don't remember what it was. All right, whatever. All right, times 6. The biggest part of this problem is realizing that now we are 6 months after, and t does not equal 2. And we can go ahead and type that again into our calculator here. So we have 100,000 times e to the, let's see, this number here. Oh, no, I was way off with negative 0.4. It's okay, so it's this number here times 6. We hit enter there. So our sales per month is going to be 71,554 per month after 6 months of not advertising. Okay, so there's some examples for you on exponential growth and decay. I hope this helps, and we'll see you in class.